On the slide I'm about to show you is perhaps one of the most influential letters ever written. The date is August 2nd, 1939, and the author is writing to President Franklin Roosevelt. In the letter, the author is proposing that the element uranium be turned into a new and important source of energy through the creation of a nuclear chain reaction so that extremely powerful and new types of bombs can be developed and constructed. Interestingly, the author is none other than Albert Einstein. This is a picture of the mushroom cloud over Nagasaki on August 9th, 1945. Between 60 and 80,000 people perished in its aftermath. At its height, the Manhattan Project employed over 130,000 people and cost over $2 billion to develop the bomb. This was the largest and most complex project ever undertaken in its day. The reason I'm discussing this is that despite the great tragedy, the developments that led to the creation of the atomic bomb are the foundation for modern chemistry. I mentioned before that Albert Einstein wrote the letter to President Roosevelt suggesting the development of atomic weapons. That was Albert Einstein's only contribution to the Manhattan Project and the development of nuclear weapons. Interestingly, despite that, Einstein regarded this as one of the greatest mistakes of his life. Unit 2 will cover atomic theory and the structure of the atom. The topics we will cover in this unit will start with electromagnetic radiation and the behavior of light. This will be followed by blackbody radiation and the photoelectric effect, which are two seminal experiments that gave us an understanding of the nature of light. This will be followed by the de Broglie wavelength and the Heisenberg uncertainty principle. The de Broglie wavelength gives us a description of the wave behavior of matter. And the Heisenberg uncertainty principle is important in the development of modern chemistry and physics. And additionally, it sets a limit on what we can know and learn about a system. Next, we will look at the Bohr model of the atom, which would be a review of high school chemistry, and we will end with quantum mechanics and a description of atomic orbitals, which leads us to the beginning of modern chemistry. This unit will help us to understand how elements behave and interact with one another. Rainbows, such as the one shown in this slide, are meteorological phenomena caused by the refraction of sunlight through water droplets suspended in the air. As we can see here, the colors of the rainbow are red, orange, yellow, green, blue, and indigo. In a process similar to the way in which rainbows are formed, white light can be separated into its component wavelengths using a prism. This occurs because the speed of light changes as it moves from one medium, such as air, to another medium, such as the glass in the prism. The slowing down of the speed of light results in refraction or bending of the light. The degree of bending depends on the wavelength of the light. And so in this way, white light is dispersed or separated into its individual component wavelengths as it passes through the prism. One way of characterizing light is to describe it as a wave, and therefore we must be familiar with the properties of waves. The first property is the wavelength, given by the Greek symbol lambda. The wavelength is the distance between two successive crests or troughs. The second property is the frequency, which is given by the Greek symbol nu, nu. And the frequency is the number of wave crests that pass over the origin every second. The wavelength and the frequency are related by the speed of the wave, given by the symbol u. The last property is the amplitude, which is the vertical distance from the midline of the wave to the peak or trough. So that would be this distance. Light, which is a form of electromagnetic radiation, is a special type of wave because it has two components. One component is the electric field component, which we see here in blue, and the other component is a magnetic field component, which is shown in red, and is oriented 90 degrees from the electric field component. Just like with regular waves, the wavelength and the frequency are related to the speed, but in this case, the speed of light in a vacuum is a constant at 2.9979 times 10 to the 8 meters per second. The frequency is generally given in hertz, or inverse seconds. The electromagnetic spectrum ranges all the way from radio waves, which have the longest wavelength and are the lowest in energy, up to microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and all the way up to gamma rays, which have the shortest wavelength and have the highest energy. Examples of radio waves include AM and FM radios and televisions. Examples of microwave radiation are microwave ovens. In between radio waves and microwaves, we have cell phones, which just sit at the border between the two. For infrared radiation, the example we have are the infrared remote controls that we use to control televisions, for example. Next highest in energy, we have visible light, which as we can see here, actually forms a very small part of the electromagnetic spectrum. The next highest type of radiation is ultraviolet light, which is often found in sunlight and is responsible for causing skin cancer. Here we also see another example of UV light, which is used to cure the white fillings that we use when we have cavities. Next highest energy are X-rays, which are used to make medical X-rays. And finally, we have gamma rays, which have the shortest wavelength and have the highest energy. CBC Radio 1 broadcasts at 106.5 MHz, where this value represents the frequency, nu, of the signal. In this example, we are asked to calculate the wavelength, lambda, in meters, nanometers, and angstroms. The strategy we'll use in this question is to start with the equation that links the wavelength and the frequency to the speed of a wave, namely c equals lambda times nu, where c is the speed of light, which is a constant, so we know this value. Nu is the frequency which we were given, and therefore we have to solve for lambda, the wavelength. Rearranging the equation gives us lambda equals c divided by nu. Substituting the values, we see that the speed of light, which is a constant, is 2.9979 times 10 to the power 8 meters per second, and nu is the frequency, which is 106.5 times 10 to the power 6 seconds to the negative 1. You'll see here that we've converted the frequency, which was originally given in megahertz, to the frequency in hertz, or equivalently seconds to the negative 1. Looking at the units, we see that the seconds to the negative 1 cancel on the top and the bottom, leaving us with units of meters for the wavelength, which is the correct unit for wavelength. Plugging these numbers into our calculator gives us a value of 2.8149 meters, and rounding to 4 significant figures, since this is the smallest number of significant figures in our data, gives us 2.815 meters, which is our final answer for the first part of this question. Checking our work, we'll note that 2.815 meters is within the range expected for radio waves. In order to convert our answer to nanometers, we have to remember the conversion factor, and as you recall, 1 nanometer equals 10 to the minus 9 meters. So starting with the answer that we calculated previously, we have 2.8149 meters, and converting to nanometers, we would want to divide by 10 to the minus 9, because there's 10 to the minus 9 meters equals 1 meter. Looking at the units, we see that the meters cancel on the top and the bottom, leaving us with units of nanometers, which is what we are interested in calculating. Plugging this into our calculator, we see that we have 2.8149 times 10 to the 9 nanometers as our answer. And rounding to 4 sig figs again gives us 2.815 times 10 to the power 9 nanometers. Now, if we want to convert our answer to angstroms, we have to remember the conversion factor for angstroms. And as you'll see, 1 angstrom equals 10 to the minus 10 meters. So starting with our answer that we calculated previously, we have 2.8149 meters dividing by 10 to the minus 10 meters. We see that, again, the meters cancel on the top and the bottom. And plugging this into our calculator, we have 2.8149 times 10 to the power 10 angstroms. Rounding to 4 sig figs again, we have 2.815 times 10 to the power 10 angstroms as our final answer.